Hey there, and welcome back to the channel. If you're anything like me, you probably learned in school that our planet Earth is kind of like an onion, or maybe a jawbreaker, made up of 4 distinct layers. You've got the crust we live on, the gooey mantle beneath that, the liquid outer core, and the solid inner core right at the center. It's a neat and tidy picture that has been in textbooks for decades. But what if I told you that picture is incomplete? What if the story of our planet's interior has a brand new chapter we're only just beginning to read? Because, well, it does. Recent discoveries have completely shaken up our understanding of what lies thousands of kilometers beneath our feet. Scientists, using some incredibly clever techniques, have found evidence of something else lurking in the heart of our world. It's official, the Earth does not have 4 layers but 5. A so-called innermost inner core hidden beneath our feet has been discovered. This isn't just adding a new line to a diagram, it's fundamentally changing how we think about the formation and history of our entire planet. It's like finding a secret room in a house you thought you knew completely. So what exactly is down there? How did scientists even find it when we can't physically go there? And what does this 5th layer tell us about Earth's past and future? Today we're going on an incredible journey to the center of the Earth, peeling back each layer one by one, from the familiar ground we walk on to the mysterious newly found heart of our world. We'll explore the extreme conditions, the mind-boggling physics, and the groundbreaking science that is rewriting our planet's story. So grab your virtual heat-proof suit, because things are about to get intense. Alright, let's start our journey at the surface, on the layer we know and love best, the crust. Think of the crust as the Earth's skin. Compared to the other layers, it's incredibly thin, like the peel of an apple. It's where we live, build our cities, grow our food, and have all of our adventures. It's the solid ground beneath our feet. But solid is a bit of a relative term when you look at the grand scale of our planet. This layer is what makes Earth, well, earthy. The crust isn't one solid piece. Instead, it's broken up into massive chunks called tectonic plates. These plates are constantly, albeit very slowly, drifting around on the layer below. The crust comes in 2 main flavors: continental crust, which is thicker and less dense, making up our continents, and oceanic crust, which is thinner, denser, and lies beneath our oceans. The continental crust is what forms the land masses, rising high above sea level because it's more buoyant, like a thick piece of styrofoam floating in water. This is the layer where all the geological action we can see happens. Mountains are pushed up when plates collide, like the Himalayas, which are still growing today. Deep ocean trenches are formed where one plate slides under another. The movement of these plates, grinding against each other, is what causes earthquakes. It's a dynamic, ever-changing surface that shapes the world we see around us, from the highest peaks to the deepest parts of the sea. Everything we've ever mined, every fossil we've ever found, comes from this incredibly thin layer. It's rich in elements like silicon, oxygen, and aluminum. While it might seem vast to us as we walk on it, the crust only makes up about 1% of the Earth's total volume. It's a fragile, brittle shell, floating on a sea of much hotter, much stranger material. So while it's our home, it's really just the very beginning of our journey downward. The thickness of the crust varies quite a bit. Under the oceans, it might only be about 5 to 10 kilometers thick. That's thin enough that if you could somehow survive the pressure and cold, you could drill through it relatively quickly. But under major mountain ranges, the continental crust can be up to 70 kilometers thick. It's like the root of the mountain extends deep into the planet. This variation is a key part of the whole plate tectonics puzzle. Despite its relative thinness, the crust holds the entire history of life on Earth. The layers of sedimentary rock are like pages in a book, telling stories of ancient oceans, long-extinct creatures, and dramatic climate shifts. Every canyon wall, every road cut, is a glimpse into this planetary biography. It's the only layer we can directly study and touch, which makes it incredibly special. But to understand the forces that shape the crust, we have to go deeper. The earthquakes, the volcanoes, the very movement of the continents, all of these are driven by the immense heat and pressure from the layers below. The crust is essentially just along for the ride, a passenger on a much larger, more powerful engine. It's a beautiful, complex, and sometimes violent place to live. So as we leave the familiar world of the crust behind, remember that everything we experience on the surface is a direct consequence of the hidden world beneath. The ground isn't as solid as it seems. It's a thin, breakable shell on a planet that is very much alive. Now, let's breach that shell and descend into the next layer, the mantle. Leaving the crust behind, we now sink into the mantle. And this is where things start to get really weird. The mantle is the thickest layer of the Earth, making up a whopping 84% of our planet's volume. It's a nearly 3,000 kilometer thick region of hot, dense silicate rock. But here's the tricky part. It's not really a liquid, but it's not entirely solid either. It's what geologists call a plastic solid. Imagine a substance like very, very thick hot asphalt or silly putty. Over short periods, it acts like a solid. If you could hit it with a hammer, it would shatter. But over vast geological timescales, millions of years, it flows. This slow churning movement is called convection. Hotter, less dense material from deep within the mantle rises, cools as it nears the crust, and then sinks back down again. It's like a giant planetary-scale lava lamp. These convection currents are the engine that drives plate tectonics. The slowly flowing rock of the mantle drags the brittle crustal plates along with it, causing them to drift across the planet's surface. This is what moves continents, opens up new oceans, and closes old ones. So, when you think about earthquakes or volcanoes, you're really thinking about the symptoms of this massive, slow-motion churning happening deep within the mantle. This is also where magma comes from. In certain spots, known as hot spots, plumes of extra hot mantle rock can rise all the way to the surface and melt through the crust, creating volcanoes. The Hawaiian Islands are a perfect example of this. The Pacific Plate is slowly moving over a stationary mantle hotspot, and as it does, the hotspot punches through the crust, creating a new volcanic island in a chain. The mantle is divided into two main parts, the upper mantle and the lower mantle. The upper mantle is cooler and more brittle, and it actually includes the very bottom part of the crust in a region called the lithosphere. Below that is the asthenosphere, which is the really gooey plastic part of the upper mantle where most of the flowing happens. It's a zone of weakness that allows the plates of the lithosphere to slide around. As you go deeper into the lower mantle, the pressure becomes absolutely immense. The atoms in the rock minerals are squeezed so tightly that their crystal structures change, becoming much denser. The temperatures here can reach over 3,000 degrees Celsius. It's a place of extreme physics, where our everyday understanding of materials just doesn't apply. The rock down there behaves in ways that are difficult to even imagine. Scientists study the mantle indirectly. Since we can't drill down that far, we rely on seismic waves from earthquakes. The way these waves travel, how they speed up, slow down, or bounce off different boundaries, tells us about the composition and state of the material they're passing through. It's like giving the Earth an ultrasound, using the vibrations from earthquakes to see what's inside. So, the mantle isn't a fiery sea of lava, like it's often portrayed in movies. It's a realm of incredibly hot compressed rock that flows on a timescale we can barely comprehend. It is the powerful hidden engine of our planet, constantly reshaping the surface we live on. Its slow, relentless motion is the reason our world looks the way it does today. With that, let's continue our descent and breach the boundary into the planet's metallic heart, the outer core. We've now traveled about 2,900 kilometers down, and we've reached a truly alien environment, the outer core. As we cross the boundary from the rocky mantle, everything changes. We are now in a vast, turbulent ocean made almost entirely of liquid metal. The primary ingredients are iron and nickel, with a few other lighter elements mixed in. The sheer scale of it is mind-boggling. It's a layer over 2,200 kilometers thick. The temperatures here are staggering, ranging from about 4,000 to 5,000 degrees Celsius. It's so hot that even with the immense pressure, the iron and nickel can't solidify. They exist as a molten, flowing liquid. But this isn't a calm, placid sea. Just like in the mantle, there are powerful convection currents here, but they are much faster and more chaotic. Hotter, less dense liquid metal rises, cools, and sinks, creating massive swirling eddies of molten iron. This churning, electrically conductive fluid is the source of one of the most important features of our planet, the magnetic field. This process is called the geodynamo. As the liquid iron flows and swirls, it generates powerful electrical currents. And as you might remember from physics class, moving electrical currents create magnetic fields. The Earth's rotation helps organize these currents, creating the giant magnetic field that surrounds our planet. This magnetic field is our planet's invisible shield. It extends far out into space, forming a protective bubble called the magnetosphere. This shield deflects most of the harmful charged particles streaming from the sun, known as the solar wind. Without the outer core and the magnetic field it generates, the solar wind would strip away our atmosphere, boiling our oceans and leaving the surface exposed to deadly radiation. Life as we know it simply could not exist. So, you can thank this deep hidden ocean of liquid metal for the air you breathe and the water you drink. It's also what makes your compass point north. The magnetic field isn't perfectly stable though. The chaotic movements in the outer core cause the magnetic poles to wander over time, and every few 100,000 years, they can even completely flip. We know this from studying the magnetic signatures locked in ancient rocks. How do we know the outer core is liquid? Again, it comes down to seismic waves. There are two main types of waves from earthquakes: P waves, pressure waves, and S waves, shear waves. P waves can travel through both solids and liquids, but S waves can only travel through solids. When a big earthquake happens, observatories on the other side of the planet detect the P waves that pass through the core, but not the S waves. This S-wave shadow zone is our smoking gun evidence that the outer core is liquid. The boundary between the solid mantle and the liquid outer core is called the Gutenberg discontinuity. It's one of the most dramatic boundaries inside the Earth. Crossing it means going from solid silicate rock to liquid iron-nickel alloy. The density literally jumps, and the physical properties of the materials couldn't be more different. It's a transition zone of incredible complexity that scientists are still working to fully understand. So, this roiling superheated sea of metal is more than just another layer. It's the source of a force field that protects our entire planet, making life on the surface possible. It's a dynamic, powerful, and utterly essential part of the Earth system. Now let's take the final plunge through this liquid metal ocean to the most extreme location on the planet, the inner core. After traveling through more than 2,000 kilometers of liquid metal, we arrive at the very center of our planet, the inner core. And here we encounter a great paradox. We've reached the hottest part of the Earth, with temperatures estimated to be around 5,200 degrees Celsius. That's hotter than the surface of the sun. And yet, despite being hotter than the liquid outer core, the inner core is a solid. A solid ball of, you guessed it, mostly iron and nickel. How can this be? How can something get hotter and turn from a liquid back into a solid? The answer is one word: pressure. At the center of the Earth, the pressure is absolutely astronomical. It's more than 3.6 million times the atmospheric pressure at sea level. All the weight of the entire planet, all the rock of the mantle and crust, all the liquid metal of the outer core, is pressing down on this central point. This immense pressure squeezes the iron atoms so tightly together that they are forced into a solid crystal lattice, even though the temperature is well above iron's normal melting point. The pressure is so powerful that it overrides the thermal energy of the atoms, locking them in place. It's a state of matter that is truly hard to wrap your head around, where extreme temperature and extreme pressure are in a constant battle, and pressure wins. The inner core is a relatively small sphere, with a radius of about 1,220 kilometers, making it roughly 70% the size of the Moon, but it is incredibly dense. Even though it's small, it accounts for a significant part of the Earth's mass. We believe it's been slowly growing over billions of years as the Earth gradually cools. As the liquid outer core loses heat to the mantle, iron crystals freeze out at the boundary and sink, adding to the solid inner core. This process of solidification is incredibly important. As the iron crystallizes, it expels lighter elements into the liquid outer core. This makes the remaining liquid more buoyant, which helps to drive the convection currents that generate our magnetic field. So, the very growth of the solid inner core is a key part of what keeps the geodynamo engine running. It's a beautifully interconnected system. Like the other deep layers, we study the inner core using seismic waves. By analyzing the subtle ways that P waves speed up as they pass through the inner core, scientists can learn about its density and composition. One of the most fascinating discoveries made this way was that seismic waves travel slightly faster when moving parallel to the Earth's axis of rotation than when moving parallel to the equator. This suggested that the iron crystals in the inner core weren't arranged randomly. They had a preferred orientation, a texture, or an anisotropy. This alignment was a huge clue that the inner core wasn't just a simple uniform ball of metal. It had a structure. It had a history recorded in its crystals. And it was this very clue that would eventually lead scientists to question if there was something even deeper to the story. So, here we are, at what was long considered the final frontier of our planet's interior. A solid ball of iron, hotter than the sun, held in its solid state by unimaginable pressure, spinning in the center of a liquid metal ocean. For decades, this was the end of the journey. But science, as it so often does, found a way to look even closer and found that the story wasn't over. The center of the center had a secret of its own. For a long time, the solid inner core was as deep as we thought we could go. But some seismologists noticed nagging inconsistencies in their data. The seismic waves passing through the very center of the core didn't behave quite as expected. There was something different about the heart of the heart. This led to a hypothesis first proposed decades ago, that there might be another distinct layer hiding in plain sight. The challenge was proving it. The signal from the very center of the Earth is incredibly faint and difficult to detect. You need a seismic wave from an earthquake to travel directly through the center of the Earth and be picked up by a seismograph on the exact opposite side of the planet. And then you need that wave to bounce back, travel through the core again, and be detected back near its origin. These are called reverberating waves. Recently, researchers from the Australian National University had a breakthrough. They developed a technique to stack the signals from hundreds of these reverberating waves from many different earthquakes. By combining the data, they could amplify the faint signal from the very center, creating a much clearer picture. It was like using a new kind of planetary stethoscope to listen to the Earth's heartbeat with unprecedented clarity. And what they found confirmed the old hypothesis. They detected a clear change in the structure of the iron right at the planet's center. This change marks the boundary of a new, distinct layer, the innermost inner core. It's a solid ball within the solid inner core, with a radius of about 650 kilometers. The difference between this new layer and the one surrounding it isn't about composition, it's all about structure. The key difference is the alignment of the iron crystals. In the outer part of the inner core, the iron crystals are aligned roughly parallel to the Earth's axis of rotation. But the seismic data suggests that in this new innermost sphere, the crystals are aligned at a different angle, perhaps around 50 degrees from the axis. It's the same material, but the texture of the grain is different. Why would the crystal alignment change? The leading theory is that it represents a record of a major ancient event in Earth's history. Perhaps there was a significant change in the way the inner core was growing, or a dramatic shift in the global tectonic regime billions of years ago. This change in conditions could have altered how the iron crystals formed and settled, leaving a permanent structural signature. This discovery is profound. It means the center of our planet is not a simple uniform sphere. It has layers of history, like tree rings. The innermost inner core could be a fossilized record of a dramatic period in our planet's evolution, a time when the forces shaping our world were very different. By studying it, we might be able to unlock new secrets about how Earth formed and became the life-sustaining planet it is today. So, our journey to the center of the Earth has revealed a final hidden layer. A world within a world, a solid sphere of iron with a different grain, hinting at a forgotten chapter in our planet's deep past. It's a testament to human ingenuity that we can uncover such secrets from thousands of kilometers away, using nothing but the faint echoes of earthquakes. The Earth, it turns out, is even more complex and fascinating than we ever imagined. So, where does this leave us? Well, for one thing, it might be time to call up the textbook publishers. The old familiar four-layer model of the Earth is officially out of date. We now have compelling evidence that our planet has 5 distinct layers: the crust, the mantle, the outer core, the inner core, and now the innermost inner core. Each layer tells a part of our planet's incredible story, from the shifting continents on the surface to this newly discovered mysterious heart. It's a beautiful reminder that science is never settled. It's a process of constant discovery and refinement. This isn't just a piece of trivia. Understanding the deep structure of our planet is fundamental to understanding everything about it. It helps us comprehend the magnetic field that protects us, the tectonic activity that shapes our world, and the very long-term evolution of Earth as a habitable planet. This new layer is a puzzle piece we didn't know we were missing, and scientists are just beginning to figure out how it fits into the larger picture of our world's 4.5 billion year history. It opens up new questions and new avenues for research that will keep geophysicists busy for decades to come. So now, you know, far, far beneath your feet, there's a whole world of secrets inside our planet. A place hotter than the sun, where metals are solid and liquid at the same time, and where the story of our planet is still being written. Don't you think our planet is so fascinating? Thanks so much for joining me on this incredible journey to the center of the Earth. If you enjoyed it, you know what to do. And as always, thanks for watching.